not too bad, right? Once you get the hang of hypothesis tests, right? And we'll cover did it? I'm sorry, I'm getting my two classes mixed up. Have I talked about type 1 and type 2 error yet?
It was on the homework.
It was in the homework, okay, but I haven't really talked about that in much detail. That plays a large factor in choosing your alpha, okay? And maybe I won't get to talk about it today. It might come towards the end. But your choice of alpha depends on how you feel about type 1 and type 2 error. Okay? You know, arbitrarily 0.05 has ended up to be the standard alpha that we generally select. You are allowed to use alpha 10%, alpha 1%, anything in between. 5% seems to be the most common alpha that we use. But you know, when I talk about type 1 and type 2 error, that plays a role in your choice of alpha. Basically, you're going to have to make a call. Is type 1 worse than type 2, or is type 2 worse than type 1? If type 1 is worse than type 2, you choose a small alpha, and if it's the other way, you would choose a large alpha. Rule of thumb. Okay, well, I'll talk about it in greater detail. Okay, but for the rest of today's lecture, I'm going to do chapters 9 and 10. Okay. And here we do chapter 9 and 10. These are hypothesis tests. For categorical data. Okay, so the t-test uses numeric data. Paired t-test, still numeric data. Wilcoxon-Mann-Whitney test, numeric data. All of those tests that we've done use numeric data. What do we do when we have categorical data? Okay. Well, when you have categorical data, you are now no longer dealing with means and standard deviations. You have proportions or you have counts. Okay, so it might be what proportion of students who take statistics, what proportion are male? Okay, and then we would get that's categorical, right? You're either male or not male, male or female, and so that's a categorical data, and then you produce a proportion. Okay, there's no mean, there's no standard deviation of the data itself, so we're dealing with that. Okay, so our first thing is we have confidence intervals for proportions. Okay, and basically you take a sample and you get a sample proportion. P hat. Okay, so if you have so let's say your sample is 100 people, and you have 47 males. Then your P hat is 47 over 100 equal to 0.47. Simple enough. Okay, we can, based on this, we can create a confidence interval. If we say this is a random sample taken from the population, can we create a confidence interval for the true proportion P? Okay. So, based on our sample, can we make a confidence interval for the true population proportion P? So the concept is very similar to confidence intervals for the true population mean mu, except now we're doing it for P, the population proportion. Okay, this is where our book does something, again, atypical from most other textbooks that I've seen, okay? So most other textbooks I've seen use p hat as the basis of our confidence interval. And so this is an aside. Aside, a 95% confidence interval for p generally looks like p hat plus or minus 1.96 times the square root of p times 1 minus p over n. So if you ever take another statistics class and you were to do confidence intervals for p, it will probably look like this. Okay. Our textbook does something a little bit different. Not wrong, just less common, and I understand why they're doing this. But rather than p, they use p squiggle, p tilde, okay, as our basis here, okay. And p squiggle is x, y, I don't know. I'm just putting in a number here. Y plus 2 over n plus 4, okay? So over here, our p hat was 47 over 100. Our p tilde, or p squiggle, would be 47 plus 2 over 100 plus 4. So we would use 49 over 104. In this situation, it doesn't make a huge difference. 47 divided by 104, I'm sorry, 49 divided by 104 is 0.4711, or 0.4712. Okay? Not a huge difference. Not a huge difference. Right? The confidence interval, a 95% confidence interval, is going to be p tilde plus or minus 1.96 times the square root p squiggle times 1 minus over n plus 4. Okay. So I say I get 0.4712 plus or minus, plug all of this in. Plus or minus 0.0959. 0.0959 plus 0.4712. The confidence interval goes from 0.5671 0.3753. Oh, sorry. And that's my resulting confidence interval. Does that match? I don't know if you guys did the math, but I think it should. I think I did this correctly. Yeah. Okay. All right, and then so we would say I am 95% confident that the population proportion P is between 0.3753 and 0.5671. Do we have evidence that the proportion of males is not 50%? If I ask you that question. So based on our confidence interval, is there evidence that the proportion of males is not 50%? No, because 50% is inside my interval, so I don't have evidence that it's not 50%. Even though my sample was only 47% males, it's not that big of a deal. Okay. Alright, so this is that's the process to do a confidence interval for P. Is that okay? We'll just use 95% confidence interval for P. We won't bother with other confidence intervals for P.
Would the only thing that changes be the 1.96?
If we use P tilde, technically a couple other things change. Okay.
Never mind.
Don't worry about it. Yeah, that's why it's not worth it. Huh?
So we're using that.
If you use this, then only the 1.96 changes. Okay. Yeah. The reason, and so let me just tell you why the book chooses to use P tilde. Okay. Sometimes you're trying to make a confidence interval for something rare. Okay. It's like, what percentage of people have 6 fingers? Okay. Maybe you, 6 fingers on one of their hands or something. Okay. Maybe you survey 300 people. Okay. 300 people, and no one in that group has 6 fingers. Okay. Does that mean? So what would happen is your p hat would end up being 0. You would have 0 over 300. Your p hat is 0. You would end up having no standard error because you have a 0 times a 1. And then so your confidence interval is just 0. But does that mean no one in the world has 6 fingers? I don't know, okay? Probably, I'm sure there's been documented cases of somebody having 6 fingers. So, so what P tilde does is it artificially adds to what you've seen. Okay, so it says whatever number you've seen, we're going to say you saw 2, okay? And then no matter how many people you saw, we're going to add 4 to that, okay? So then that changes your number to saying I saw 2 out of 304 people, okay? And then the other hand also, on the other hand, it works. So if we said, what proportion of people in the world have 5 fingers on their left hand or whatever, maybe you interview 300 people and you get 300 out of 300, okay? Again, you would get a proportion of 1, no standard error. Is that what happens? No. This says, okay, you saw 300 out of 300, we're going to add 2 to the numerator and add 4 to the denominator, so it's going to say 302 out of 304. You get something like 99 point something %. And then so you get a tiny bit of a standard error, and then you can create a confidence interval, okay? In those extreme circumstances, there's a chance that your confidence interval goes negative or over 1, all right? Just truncate your confidence interval at 0 and 1 if that were to happen, okay? So if you get, if you do this thing where you get 300 out of 300, your confidence interval might go from, you might say I'm 95% confident that the proportion is between 0.99 and 101% or something, okay? Don't, you look stupid if you say 101%, so just say it's between 0.99 and 1, okay? So that's that, okay? So the P tilde is kind of this artificial thing that that they do to the proportion, so you don't get these extreme boundary scenarios. Okay. Again, this is one of the few textbooks, I mean, I haven't studied that many textbooks, but so I haven't seen it in other textbooks. That's why they do it. But chances are, if you were to take another course, they will probably use this. Okay. But the warning being, if you get a sample so that's confidence intervals for proportions. In my opinion, pretty straightforward because it's not very different for confidence intervals for means. It's just the formula has changed. So the other big part is then we do the chi-squared test. Chi-squared test. It looks like chi, but it's chi because this is based on the Greek letter chi. So it's the chi-squared test. Chapter 9, we do the chi-squared test for proportions. And then in chapter 10, we do the chi-squared test for independence. Okay, so when we do the chi-squared test for proportions, our null hypothesis says we have these proportions in mind. And we want to see how well does the data we observe fit those proportions we have in mind. Okay? So we have proportions in mind. Oops, sorry. We ask how well, actually it should be the other way. How well do those proportions fit the data we observed? And because we're essentially asking how well do those proportions fit the data we observe, this chi-squared test for proportions is also known as the chi-squared goodness of fit test. Chi-squared goodness of fit test. Because it should be chi-squared how well does the I don't know, how well fit? I don't know. We don't say what is the goodness of the, I don't know. But you can't say wellness because that means a whole nother thing, right? It's like health. So, anyway. Goodness of fit test, we're asking how well do these proportions fit the data we observe. So it could be, one example, we want to test, does a coin flip fair? Does a coin flip fairly? I don't know. Are the results of a coin flip fair? Are they not? Okay. So in our case, the null hypothesis would be that the proportion it lands heads is equal to 0.5, and the proportion it lands tails is equal to 0.5. That would be our null hypothesis. The alternative is that the proportion it lands heads doesn't equal 0.5, which consequently means the proportion it lands tails isn't 0.5 either. Okay, because you can't have a scenario where the proportion it lands heads isn't 0.5 and the tails is 0.5. Or it could be, does a die roll fairly? Fair?
Fairly.
Fairly. Okay, does a die roll fairly? Alright, no. And then we would say the proportion that it lands on 1 is equal to 1 out of 6. The proportion it lands on 2 is equal to 1 out of 6. The proportion it lands 3 is equal to 1 out of 6. The proportion it lands 4 is equal to 1 out of 6. And 5 of the faces is 1 out of 6, and the alternative is that at least one of those proportions is wrong. Right. Okay, when you have more than one proportion category, when you have more than one, the alternative has to be this non-directional, at least one is wrong. Okay, this is non-directional. If you have more than one category, so in this case we have 6 faces. I'm sorry, if you have more than 2 categories, you have to have a non-directional alternative. With the coin flip, this one is a non-directional alternative, but there's only 2 categories. You can have a directional alternative when there's only 2 categories. Alright, so when there's more than 2 categories, alternative must be non-directional. With 2 categories, alternative can be directional. Okay? Because if I were to say the proportion of heads is greater than 0.5, then I know that means the proportion of tails must be less than 0.5. Okay? If I have too much of one proportion, it forces the other proportion to be less. In this situation, if I were to say it rolls the number 6 too often, and I say the proportion of 6 is greater than 1/6, where are you going to, what other category are you going to reduce? Okay? You know, does that mean it rolls number 1 less often, or number 3 less often, or all of the other ones less often? You can't, you don't know where the extras are coming from, so you can't choose that. If you want to say it rolls the number 6 too often, then you have to collapse the other categories and turn it into a 2-category response. How often it rolls number 6 should be equal to 1/6. How often does it not roll 6 will be 5/6, and now you have 2 categories, and you can have directional order. Okay. The nulls don't always have to have 0.5, 0.5, or all equal things. It could be something like I don't know, the proportion of you know, if you have cars or something, okay, it could be the proportion of, you know, American cars is equal to 0.3, and the proportion of European is 0.4, and the proportion of Asian cars 0.3 or something. You could have different proportions. Are those the only car producers that we happen to see in TUS? I think so. Something like that. Okay. So you can set different things. So if this is your null hypothesis, then your alternative would be at least one of the proportions is wrong. Okay. Non-directional. Okay, so let's say we were doing this American versus European versus Asian cars. Let's say So somebody says, I think 30% of the cars on the road are American, 40% are European, and 30% are Asian. Asian cars in America are only from Japan and Korea, right? Do we have, is there Chinese? Not in the US. Okay. Alright, so let's say we go out and we collect data, alright? And then, and so we have American cars and European and Asian. Okay, so somehow we gather random data. I don't know how you would do this, in all honesty. It'd probably be very challenging. Okay, so let's say you see 45 American cars and 40 European cars and 50 Asian cars. So that's a total of 135 cars. And the question is this data, how good or how well do these proportions fit the data we observed? That's what we want to know. Okay. Does our data deviate far enough from this for us to reject this null hypothesis? Or is it possible that, you know, our sample just ended up this way by random chance? Is it possible that these proportions actually hold and that when we took a sample of 135 cars, we happen to see this makeup of cars instead? Is that possible? Did that happen by random chance? Okay. So, right, our p-value is the probability of observing our data if the null hypothesis were true. So, to figure that out, we're going to calculate a chi-squared statistic, and this is the difference between the observed minus the expected squared over expected, and we sum that up. Okay, so we do observed minus expected over expected. So our data is what we observed. Okay, I'll write O is observed, B is expected. Okay, so how many cars do we look at total? We saw 135 cars. If our proportions are correct, I should see 30% of the 135 cars should be American, right? So I would do 135 times 0.3 is equal to 40.5. So if my proportions were correct, I would expect to see 40.5 of my cars to be American. I happen to observe 45 cars to be American. Is that too much of a deviation, or is that possible from random chance? I do the same thing for the other one. 135 times 0.4, I would expect 54 of the cars to be European if these proportions were correct. And I do 135 times 0.3 again, I get 40.5. I expect 40.5 of the cars to be Asian. So I do observed, and I have the expected. Alright, is everyone okay with how we get the expected numbers? Alright, so now I calculate my chi-squared statistic. So what did I observe? I observed 45 American cars. I expected 40.5 cars. I square that difference, and I divide by 40.5. I do the same for the next category. I observed 40. I expected 54. I square that difference, and I divide by 54. and I observed 50, I expected 40.5. I square that difference and I divide by 40.5. Alright, so I do this. That. Alright, my chi-squared statistic, I end up getting 6.358. Is that okay? Alright, so with this, now I go to my chi-squared table. Chi-squared table is based off of a squared normal distribution. Believe it or not, there is a central limit theorem assumption going on underneath here. I'll explain it in a moment. Don't worry too much. So anyway, flip to table, what is it?
9.
9. Okay. For chi-square distribution, you also need the degrees of freedom. Okay. Degrees of freedom is the number of categories minus 1. So I have 3 categories of cars: American, European, and Asian. So I have 2 degrees of freedom. Is that okay? Alright. And so I look up 2 degrees of freedom, and what would my p-value end up being? My test statistic is 6.358. That is in between 5.99 and 7.82. So my p-value would be in between 0.05 and 0.02. So if these proportions were actually true, if the proportion of cars on our roads in the United States was 30% American, 40% European, and 30% Asian, what is the probability that my data would produce this kind of sample or something even more different from this? Well, that would happen between 2 and 5% of the time. Okay. So this really depends on our choice of alpha. But let's say we used alpha equal to 5%. If alpha was 5%, my p-value is less than alpha. And so we would reject the null hypothesis. And we would conclude that at least one of the proportions I have there is wrong. Okay, so we have evidence.
You don't have to double it.
No, these are for directional, non-directional alternatives. Okay, so the chi-squared table, and it says on the table itself, it says the column headings are for non-directional alternatives. If you happen to have a directional alternative, which only happens when we have 2 categories and you specify a direction, and you have to check directionality there also, then you take the column headings and divide by 2. Okay? So the only weakness with the chi-squared test is maybe you come to this conclusion. You say we reject the null, at least one of the categories or proportions is wrong. It just doesn't tell you which one. Okay? We don't know if it's because there's too few European cars or too many Asian cars. We don't know. Okay? Or that combination of those two things happening is enough evidence for us to reject the null. All it says is we reject the null. Alright? Is that okay? Alright, so that's the chi-squared goodness of fit test. And that's pretty much chapter 9. Chapter 9, maybe in your reading, it goes into a little bit more detail here and there, but that's essentially what's going on. Okay. You know, when I don't want to give away my quiz question, but you know, I have, like, in the, not this week, but a couple of weeks, you'll have a quiz and there's a chi-squared goodness of fit question on there, and it involves a game of chance, okay? And I don't explicitly define the proportions. You've got to read the question to figure out the proportions that you would expect. So, for example, let's say we were playing a game with a die, and I said, you know, you want to know what's the probability you roll an even number versus, you know, a number larger, you know, an odd number bigger than 2 and 1. Okay, so then there would be 3 categories. One would be even. How often should that happen? 3 out of 6, 0.5. Odd number bigger than 2. That would include 3 and 5. That should happen 2 out of 6 times. And then how often should you roll the number 1? 1 out of 6. Okay, so based on the description of the problem, you've got to figure out your proportions. I think it's reasonable, but I know it tripped up a lot of my students in the past, because in the homework they explicitly give you the proportions almost every single time. Okay, but I think it's important to be able to figure out proportions on your own as well. It's not terribly hard, but if you aren't, I guess if you're not thinking about it, it could catch you off guard. I know we're just blitzing through these sections here, but I feel like they're related enough. Okay. Chapter 10 is the chi-squared test for independence. It's highly related to the chi-squared goodness of fit test. But the main thing that happens here, chi-squared goodness of fit test, there was only one categorical variable. Chi-squared test for independence, we're asking independent of 2 categorical variables. We're asking, do we have evidence that these 2 categorical variables are independent or not? So if you have a question and you pick up that there's 2 categorical variables, then you know you're dealing with a chi-squared test for independence. Goodness of fit, 1 categorical variable, and you have proportions in mind. Chi-squared goodness of fit, chi-squared test for independence, you have 2 categorical variables, and you want to see if they're independent. The basis, okay, the basis for the work here is that if you remember the rules of probability, if events A and B are independent, probability of A and B should be equal to the probability of A times the probability of B. That forms the basis of what we use as our expected values here. Alright, so let's say we want to know, does gender have anything to do with handedness? Oh, maybe I use this quiz on the question of the quiz. Well, we'll see. Alright. Alright. Is gender related, related to handedness, or are they independent? That's what we want to know.
What does that word mean?
Huh?
What does that word mean? Handedness.
Like
Handedness,
left-handed.
left hand or right hand.
Oh.
Okay? So does being male or female have anything to do with the probability of being right-handed or left-handed? I don't know. Does it? Who knows? Who knows? Okay. So let's say we're like, I don't know. Okay. Right? Like certain things are like gender related. Color blindness is definitely higher prevalence in males than females. Things like that. Okay. Handedness though. What about that? Okay. So we go out and we collect data. All right. If we have two categorical variables, should we collect our data or summarize our data? A two-way table, contingency table. Okay, so we have male, female, left hand, right hand. And let's just say there's only two. We can include ambidextrous, I guess, but just for simplicity, let's say left hand and right hand. Let's say I observe 10 left-handed males, 50 right-handed males, total of 60 males. 12 left-handed females, 52 right-handed females for a total of 64. Well, it'll be fine. Okay, so I have a total of 124 people, 22 left-handed and 102 right-handed people. Is that okay? So this is what we observed. Okay? The chi-squared statistic, we know it's found the same way. Observed minus expected, quantity squared over expected. And we do this for our four categories, or four cells. How do we figure out the expected? There's male, female, left, and right. Okay. Overall, what's the probability, if I have 124 people and 60 of them are male, the overall probability for being male is 60 over 124. Okay? The probability for being left-handed is what? 22 over 124. Is that okay? So the probability of male and left-handed would equal, if they are independent, I would do this times this, right? Probability of A and B should be the probability of A times the probability of B. So in this case, I would do 60 over 124 times 22 over 124. I would get some number there. That would be the probability that I'm looking for. But if I want an expected count, I should multiply that number by what? The total number of people, 124. Right? So this would be the probability of this cell, but if I have a total of 124 people, that would give me the expected count there. So I'm going to take this number and multiply it by 124. Is that okay? So this is the probability of being male and left-handed. I should say my expected count is thus going to be 60 times 124 times 22 over 124 times, I have a total of 124 people. So I would multiply that into, and I would get a number there. Does that make sense? Okay. So because of math, these cancel out, so I can just do 60 times 22 divided by 124. Is that okay? And so I expect 10.645. It does. However many, let's just do 10 point. I don't know. We'll do 10.65. Okay. How many decimals you keep probably won't make a huge difference. Alright? Okay. We can do that for all of these, okay? The shortcut, so if you follow this line of thinking, and you do probability of female, probability of left-handed or right-handed or whatever, and you say male and left and the expected count, you'll find that the expected count, the shortcut, is equal to our column total, 60, 64, 22, and 102, is equal to my column total times the row total divided by the grand total. Okay, that's essentially what I'm doing here. Column total times the row total divided by the grand total, because these things cancel each other out. But all I'm really doing is the probability of male, probability of being left-handed. I multiply them together because of my rule for independence, and then I multiply it by the total, grand total to get an expected count. Is that okay? All right. And so I do that for all 4 of my cells. All right. A little secret though is that if I have 10.65 here and the total is 22 over here, what number has to go here? 11.35, right? Because those two things have to add up. And if this is 10.65, so I have 49.35 and 52.65. Okay. So what we just observed is that in our problem here, there's only 1 degree of freedom. Because as soon as one number was determined, the other numbers were locked in. Okay, so in this scenario, we only have 1 degree of freedom. The formula for degrees of freedom is actually very simple, but I'll get to that in just a moment. Okay, so there I have my observed data. I have my expected counts, and so now I can figure out my chi-squared statistic. Okay, so I do 10 minus 10.65 squared over 10.65 plus 12 minus 11.35 squared over 11.35 plus, I do the same for 49.35 plus the last one, 52.65, okay? Whatever it is, I end up getting 0.65 squared. And then, so, my chi-squared statistic tiny little 0.0935. Alright, so I'll just tell you, that's a very small chi-square statistic. Alright. Is everything so far so good? Alright, so just like every other test, we then take our chi-squared statistic, we look it up in our chi-squared table, and whatever it is, I'm going to get a p-value greater than 20%. So the degrees of freedom for chi-squared test for independence is the number of columns minus 1 times the number of rows minus 1. So for a 2 by 2 table, we have 2 minus 1 times 2 minus 1, 1 degree of freedom. Okay, so my chi-squared statistic equals 0.0935. So we would, my p-value is greater than 20%. So we do not reject the null hypothesis. And I'm embarrassed, but I did not actually write out the null and alternative hypotheses here. Can I erase this table here? Forgot. The null hypothesis for chi-square test for independent is that, in our case, would be gender and handedness are independent. We could do all sorts of variants here, but another way of stating independence is stating that the probability of a given B is equal to the probability of a given B complement. That's one way of saying. So we would say the probability of being left-handed given female is equal to the probability of left-handed given male. Okay. There's actually many ways to state independence using equations. Other ways to state independence would, if you just look back, would be probability of A and B is equal to the probability of A times B. That's also fine to state. Probability of A given B should equal the probability of A. Any variation of that. The alternative, okay, once you have an equation here, you just set that either to not equal, greater than, or less than, depending on how the question is written. Again, you can only have a directional alternative if you have only 1 degree of freedom. If we had more than 1 degree of freedom, you can't have a directional alternative. So in our situation, we could say, we could ask the question, do we have evidence that males are more likely to be left-handed? And if that were the case, the alternative would be probability of left-handed given female is less than the probability of left-handed given male. Okay, if we said males are more likely to be left-handed. But if we had multiple categories, then you couldn't do a directional alternative. Okay, so our null is this. Our alternative, we would just stick in a not equal sign. And according to this, if our data was what we had, we would not have evidence to conclude that they are not independent. Okay? We do not have evidence that they are not independent. So it doesn't prove that they're independent, but we have no reason to believe that they are not independent. Yes?
If it were directional,
Yes.
would all of the calculations be the same?
All the calculations would be the same. At the end, you would take your p-value and divide it by 2. Okay? Oh, and I guess you should check for directionality. So if we were saying males are more likely to be left-handed, then your data should show that a higher proportion of males are left-handed. Okay? So there should be a directionality check. The one very, very last thing, and this is just like I can say with one sentence, right, is that there is an underlying central limit theorem. It's hard to see, okay? But there is a condition to use the chi-squared test, and this is whether it's goodness of fit or independence, is that the expected number for all categories, if it's goodness of fit, or for all, I guess, inner cells of a table, and if we're dealing with independence, should be at least 5. Okay, and then some texts say 10. But I think our textbook says 5. Okay, so the expected number for all categories should be at least 5, and that promotes the central limit theorem. If you come across a situation where this does not hold, so you have two categorical variables, but the expected number for one of the cells is not 5, then you have to do a non-parametric test. And the book talks about it. The example that they use is called Fisher's exact test. You might run across it in the literature. We're not going to cover it in this class, but if this condition is not met, consider I forget how to spell Fisher. I think it's, how do you think? Fisher's exact test. That's if that ever happens, okay? But you know, I will only give you scenarios where this thing holds. But this is a condition you should check.
So what's GOF?
Goodness of fit test. Okay, when you have the preset proportions and only one category, I mean one categorical variable.
What does it mean? I mean, can you give an example? Like, I can now visualize